Hello, test call check 1 2 3. Hello, test call check 1 2 3. Hello, test call check.
A very warm good morning to all of you. It's a pleasure to see you all back. I was afraid that after yesterday's onslaught of information, some of you might say enough is enough, but I'm glad all of you are back. About the last session, I got some feedback that there was a lot of information. I presented many things, and many of you could not follow the details. The point is, the goal of last session yesterday was to convey to you that the field is live and kicking, and there are lots of interesting ideas that are being pursued. I did not expect you to be able to follow the details of what is being done. At the moment, many of you are not equipped with the background to understand the details, and therefore I did not provide too many details either. The goal was only to tell you that lots of things are happening, and that's the message. That was the main message, and I hope that that main message was conveyed. So yesterday we had a story which was very abstract, was at a very high level. Today's story is going to be less abstract, it's going to be more concrete, it's going to be about specific things. We are going to talk about very specific key ideas. Of course, we are not going to cover all of this. The title is Introduction to Program Analysis. The word introduction is very important because otherwise on program analysis I teach a full semester course. I just finished a course just now in this semester, right? So obviously we won't be able to cover everything, but the goal is to cover the basics in sufficient detail. I'm not going to keep it abstract today. We are going to cover in sufficient details. There are tutorial problems that we would like you to work out. There are tutorial problems that have been made available on the Google Drive. Today I will make sure that whatever we are doing, all of you understand it. If the need be, I will slow down. If the need be, I will repeat. If the need be, I may omit some topics if we run out of time. But I don't want today's session to be an abstract session. Today we are going to talk about concrete stuff, right? That's the message. So what that means is I want all of you totally invested in what we are going to discuss now. Okay, so here is an outline. We'll begin with some representative examples of applications of program analysis. Again, we have to begin with why did program analysis come into existence in the first place? What is it that we can do with it? We'll talk about from those applications, we will make some observations. We'll talk about what is program analysis, and then we are going to look at 3 concrete examples of program analysis. Something called live variables analysis, available expressions analysis, and reaching definitions analysis. So that is the goal for the day today, right? That's what we are going to cover in the entire day. I will stop in the middle of the lecture sometime. I might just say, okay, do this tutorial problem, show it to your TAs. So we have TAs today. Nisha is here, Ramya is here. Is Ramya is there. So she is the other TA. So we have 2 TAs today. They have gone through the tutorial problems, they have gone through the slides, so they should be able to help you with any doubts in the matter that we are discussing. Okay, so let's begin with examples of applications of program analysis. So we'll begin with classical optimizations, and when I say classical optimizations, these optimizations were invented So these optimizations were invented in the very first compiler that John Backus wrote in some form, not exactly in this form, but the ideas date back to 70 years, some of them. So some key ideas, and they're still being used, so you can imagine how influential they have been. Of course, lots of new things have happened. The field is not stale. but these are the basics that convey the idea of program analysis. So when John Backus and his team invented this, they didn't know that they are setting the foundation of a field called program analysis. They did these things as ad hoc techniques in 1954, and in the 70s people started building the theory. In the 70s people started building a conceptual framework that would explain what these ad hoc ideas were. So what we are going to look at is, we are going to begin not by program analysis, but by what the program analysis can do, can help you do. That is the goal of this particular section of the talk. So let's begin with a piece of code. This is an example from the Dragon book, from the book by Aho Setty-Ullman. The example is from Aho Setty-Ullman, although I have modified it in my own way. This is a piece of C code. It's a quicksort function, and as we know, what quicksort does is it finds a pivot and then it moves values smaller than the pivot to the left of the pivot, larger than the pivot to the right of the pivot, and then sorts the two partitions recursively. That's what quicksort does. Okay, but as we said yesterday, we are not interested in what the program does. We are interested in what we can do with the program. That's our goal. So we're going to focus on this yellow box, code in the yellow box. We'll leave out the rest of the code, and we want to see what is it that a compiler can do with this piece of code and what kind of information is required, and then we will try to speculate what techniques are required in order to get this information, and then we will see what are the systematic principles that allow us to get this information. That's the motivation behind taking this example, right? So yesterday we talked about control flow graphs. I hope all of you are aware of them. If not, maybe in today's break or sometime you should do the tutorial problems, the PDF that has been given to you, not the programs, of being able to construct control flow graphs for programs, because that is critical. Today's entire material is based on being able to relate a source program to a control flow graph, and that's the reason why we gave you those tutorial problems. Okay, so we will begin by looking at this piece of code. So what we do is we create a 3-address code, and we saw yesterday that what a 3-address code is. So a 3-address code essentially is a sequence of statements in which every large expression has been subdivided into smaller expressions. The values of intermediate expressions are stored in temporaries. So all variables that begin with T, T1, T2, T3, I think it's up to T6. All these variables are temporary variables. So these temporary variables have been introduced by a compiler. Okay. But in this piece of code, there are 1 to 33. So there are 33 3-address code statements representing that piece of code in the yellow box. You will see a splash of colors here. Okay. I want you to try and imagine what does this scheme of colors indicate other than joyousness, other than feeling happy. What purpose does this color coding indicate? Can you observe a pattern? Yeah? Anyone else? Common sub-expression, common operations, similar operations, okay? Yeah, so the main point is the same statement has been given the same color. So if you can see, we have the green statement is T1 is equal to 4 star n. So that's statement number 3, statement number 29, statement number 32, all these are the same piece of statement. And this is where it differs from what Aho Setty-Ullman does. In their book, they do not use the same temporaries. I use the same temporaries, and the reason will become clear as we go along. It's not a good idea to use different temporaries, but that's a different matter. We'll come back to it later. So similarly, blue expression, blue statement is 7, 15, 18 and 25. The advantage is then we don't have to talk about specific statements. In my description, I can refer to the green statement, the blue statement, green expression, blue expression, etc. So it becomes conveying ideas clear. So that's one part of it. The second part of it is, and this is a deeper observation, that the statements repeat. Right? There are multiple occurrences of the statements. Why do we need multiple occurrences? Is this repetition redundant? Can we do away with some of them? Can we delete some of them? So I have already computed the value of 4 star n in T1. Do I need to recompute it here? I have already computed the value of T2 4 star I here. Do I need to recompute it here, here, here? So the point is, when we translate a code in higher level abstraction to a lower level abstraction like this, it exposes repetition of computation. And we would like to optimize the code by eliminating this repetition. Right? So if I were to ask you, is this statement 15, is it required? I am already computing T2 is equal to 4 star I, and I am recomputing T2 is equal to 4 star I, and I am using T2 here. Is it okay if I delete this and reuse the value that's computed here? What do you think? Is it okay to delete statement 15 and use the value computed in statement 7? What is your intuition? What does your guess say? I'm not expecting an exact answer, but I just want to get a drift of your thought. You're giving me the condition, you give me the answer. You determine whether the I value changes or not. Her remark is, if the value of I does not change from here to here, then we need not recompute it. That's right. But the main question is the value of I changing? You have to determine that. How do you determine that? Yeah, so you see here, from here, there is a go to 6. Right? So the point that I am trying to drive home is, when you want to ask this question, you say, okay, this path is going from here to here, then from there and all that, right? The execution of the program need not necessarily follow the exact same sequence, because there are control transfers in between, right? The execution order could be different from the lexical ordering of the statements. And therefore, it's important for us to explicate the control flow within the program. We cannot simply say they are one after the other, so therefore they will be executed one after the other. So therefore, what we do is, so this is what I just explained, 3 address code, a simple control flow, and yet it is very undecipherable. Okay. So what we create is, we identify control flow and we create what are called basic blocks, which are maximal sequences of linear control flow. Basic blocks are the group of statements in which the control flow enters at the start of the block and leaves at the exit of the block. There is no jump into the middle of the block, nor is there a jump from the middle of the block. So if you start executing first statement, you have to execute all of them until you reach the end. That's a basic block. And we want it to be maximal. In the trivial case, every statement could be its own basic block, right? And there are situations where we construct basic blocks consisting of a single statement. But for the kind of analyses that we are talking about today, we will consider largest basic block because it will save our computation, save our effort, right? So we identify basic blocks, okay? So these are the basic blocks that we identify. How do we identify basic blocks? Well, any statement which is target of a control transfer begins a new basic block. Any statement that follows a conditional transfer begins a new basic block, and the first statement begins a new basic block. Like this, we create this partition of statements, and then we create this graph called control flow graph or program flow graph, right? So the idea is you should be able to say, you should be able to see why this corresponds to the given source code. So if we step back a bit and examine the given source code, observe here that the yellow box has a while loop. Inside that while loop there is a do while loop, there is another do while loop, and then there are some statements and there is a break here, right? Now we have to be able to relate this to show me the while loop here and show me the two do while loops here. Tell me which blocks constitute the inner do while loops and which blocks form the outer while loop. A little louder, please. Yeah, anybody? Yeah. B2 and B3, what are they? The inner do while loops, right? Where is the outer while loop? Yes, from B5 to B2. So B2, B3, B4 and B5 constitute the outer while loop. So there is an outer loop and within that there are these two loops, right? So this is the control flow graph, and now we will start examining things. Things will become a little easier for us, okay? So we begin by performing what is called local common subexpression elimination. Local means it is restricted to a basic block. And the advantage of doing so is that when we talk about a basic block, we don't have to worry about where the control flow is coming from, because we know exactly the order in which the statements are going to execute in a basic block. So we restrict our attention to a basic block and we identify the computations that are redundant within a basic block. So here in B6 and B5 we have some computations. Now can you tell me that if any of the blue computations redundant there in B6 and B5? Didn't you guys have breakfast today? Yes? Why don't you have energy then? Is it the physical energy that's lacking or is it the mental energy that's lacking? Let's take this. Is this occurrence of T2 is equal to 4 star I redundant? Obviously, because the value of I does not change. Is this instance of 4 star n redundant? No? Someone said no. Why? I am talking about this one. Why do you think it is not redundant? No, I am talking about this one, right? I have computed T1 is equal to 4 star n here. Do I need to recompute here? So it is redundant. right? Similarly here, the yellow expression is redundant, right? Because the value of j does not change. Very easy to determine, right? So we perform this optimization and we eliminate certain expressions. This is called local common sub expression elimination. This existed in the very first Fortran compiler constructed in 1954. Even now every compiler does it. Okay. Let's go to global common sub expression elimination. Let's complicate the matter a little. You know, one of the things that I tell my students in my course is that every topic and every lecture will show you that the previous lecture and the previous topic was much easier to understand. So the previous optimization was much easier, now I have something else. Global common sub expression elimination. My question is, can I get rid of, let's begin with this, T2 is equal to 4 star I, can I get rid of this, can I get rid of this? What do you think should happen? How do I answer this question? How do I even approach answering this question? So let's talk about this expression. T2 is equal to 4 star I. Is this redundant? I have computed it. Where have I computed it before? No, that's the first occurrence. So let's talk about this. Is this redundant? So we have to guarantee that between this and this the value of I does not change. Can we guarantee that? But from here we can go back. Right? Possible to go back. So the value of I changes. So your condition is not satisfied. Okay. So her suggestion is that this loop in B2 has finished and then we reach B5. How many of you agree with her? Okay, there are several people who agree with her and she is right. There is a more formal way of arguing about it. So let's talk about repeated computations in an execution path in a program. So I have this loop B2 being executed multiple times, right? And then I have this B5. After B2, I have B3, then B4, then B5. I'm asking a question, is this computation redundant? Talking about this particular occurrence at execution time. Remember, I'm talking about what's going to happen at execution time, but I am trying to map it to what happens at compile time. What program analysis does is try to bridge this gap between dynamic world and static world. Something would happen at runtime and we are trying to abstract it at compile time. And that's the beauty of program analysis, right? So here here this is a runtime and we will map it back to the compile time. So we are asking at runtime, is this computation redundant? When we ask this question, we will have to say what was the previous computation of T2 is equal to 4 star I, and it's obviously this, it's not this, right? So whenever we have multiple occurrences of a statement because of a loop in a path, and when we say compare two statements, we have to talk about the last occurrence of the previous statement and the first occurrence of the next statement. Right? There is no point in talking about the previous occurrences. There is no point in asking about the value of 4 star I and the value of 4 star I here, because 4 star I is recomputed, right? So which means that we have to think of whether the value of I is changing between the last occurrence of this statement and the first occurrence of this statement. Right? That's the first principle of static analysis. The principle is that there are multiple instances, there could be multiple instances of the execution of the same statement at runtime, and we have to talk about at compile time which particular instance should we be referring to. We do not know how many instances would be there, and we don't care. That's the beauty of program analysis. Right? So now if we abstract this out and if we say, tell me now from here to here through a path that does not go through cycles, is the value of I changing? The answer is value of I is not changing. So we can actually delete this. So when we talk about these, the value of I in between is not changing, right? So we can eliminate this as a global common sub-expression, right? Similarly, T3 is equal to A of T2. Similarly, T4 is equal to 4 star J. Similarly, T1 is equal to 4 star N. All these statements go away as redundant, right? For the same reasons. However, we have T6 is equal to A of T1 and T6 is equal to A of T1. In order to say whether they compute the same value, one could be tempted to ask a question, is the value of T1 modified between them? What is your answer? Why is it that this has not been eliminated? Is there an oversight or is there some reason for it? Is the value of T1 being modified somewhere? Do you see an assignment to T1 somewhere? No. So why has that not been eliminated? We are changing the value of J, okay, and value of N. N doesn't change. Where is N changing? N is fixed. N doesn't change anywhere. J is equal to N. I don't see where. J is equal to N. Oh, that one. But that's already done. After that, we are computing this. So, I am talking about between this and this. What happens? Okay, very good. Very good. Can you expand on it? Let's say it's 5.
Yeah, but we have used T2 is array, the same array in B2. And if T2's value is equal to T1, then there might be a change.
In B2, we are only reading, we are not writing.
Somewhere it might change.
This is the instance, right? So the point is that we are reading from location, we are reading from an index stored in T1. We are writing into an index stored in T2. Can we prove that T1 is not equal to T2? In general, we do not know. So it's possible that whatever value we are reading here, we might be writing it into the same index here. So when we talk about, so this brings out a very important principle of static analysis. When we talk about aggregate data, when we talk about arrays, we have to look at array as a whole because we cannot talk about specific indices of array. So if anywhere there is a write to an array, we will have to assume that in general any location in the array may be written into. Right? So we cannot look at this just as an expression A of T1. We just have to say we are reading from A, we are writing into A, therefore we do not know we are reading the same value of A. So what I am trying to say is that when there is a difference between scalar variables and aggregate variables, when I am writing into I I know I am writing into I. Here I am reading from a particular index of the array and I am writing into some index of the array. Now in general, I cannot say that these two indices are different, or I cannot say that these two indices are same. I do not know, because it depends on the values in the variables. Here we are not talking about what is the value in j, we are not talking about what is the value in I, we are simply saying whatever is the value I am writing something new. Here we will have to, if we talk about arrays, we will have to, if we talk about specific indices, then we will have to talk about the value of the index, something which we in general cannot do at compile time. So therefore what we have to do is, there is an array, so let's just look at this board. Where is the duster? Oh, I left it there yesterday. So look at it this way. I have an array A, this array A, and somewhere at index T2 I am reading, and somewhere at index, no, at T1 I am reading, at index T2 I am writing, right? Now the question is, in general I do not know what are the values in T1 and T2. At compile time I would not know. So therefore I will not be able to say whether in particular this location is being read or written. I will not be able to distinguish between different indices of the array. So I have to treat the array as a whole. If I am writing into any part of the array, I am possibly writing in every location or any location. If I am reading any location, then it could be any arbitrary location. So I have to view this not as A of T1, I can completely ignore this. I am reading from array and I am writing into array, and therefore I cannot guarantee that the value that I read here and that I read here is same. So in other words, technically speaking, arrays are treated index insensitively. Whatever conclusion I draw should not account for specific index, cannot account for specific index, and therefore I am unable to conclude that the value that I read here will be same as the value that I read here, right? So when we perform analysis, we have to distinguish between scalar variables and aggregate variables, right? Does that make sense? Yeah. Yes, yes, of course. If they are immutable, then we are not worried about being overwritten, right? Right. So if they are immutable, it doesn't matter. Everything is about mutable variables. If the variables are not mutable, then there isn't any interesting analysis that you are doing here, right? Okay. Any other question? So this is the global common subexpression elimination. Okay. So let's move on. Let's move on to the next thing. So let's look at other classical optimizations: copy propagation, strength reduction, elimination of induction variables. Now we will go fast on these. Okay. So observe here that I have x is equal to T3 and there is a use of x. Similarly, I have x is equal to T3 and there is a use of x. Copy propagation says that if the value of T3 is not changing in between, then the value in x here is same as the value in T3. So T3 is a copy of x and I can propagate the copy. So I can overwrite this x, I can replace this occurrence of x by T3. What is the advantage of doing that? What could be a possible gain? Unnecessary memory used will be avoided. How? No, but I am saying replace x by t3. So I am using temporary variable. Okay. Any more precise statement? So what is the advantage of replacing this x by t3? That's a concrete question. Yeah. Okay. I am still looking for a more precise characterization. Okay. Yeah. I don't know why all of you are thinking of registers. I didn't even utter the word register. This is something much simpler. Much simpler. Observe that if I replace this x by t3, where is x being used? Yeah. So there is no further use of x. So the assignment x is equal to t3 becomes a dead code. Right? I am assigning to a variable that I am not using. So I can eliminate that assignment. It's there in the title. Copy propagation and dead code elimination. So once I replace this x by t3, the advantage is that it leads to more dead code. It can lead to some assignments being redundant. Not necessary that it will always happen, but it often leads to dead code elimination. So that's the other optimization, copy propagation and dead code elimination. Okay. Now this is something very interesting. See here that the value of T4 changes with the value of J. Whenever J decrements by 1, T4 would decrement by 4. Similarly, whenever I increments by 1, T2 will increment by 4. So the values of I and T2 move in locked fashion. Values of J and T4 move in locked fashion. So if I have to compare I and J, I can possibly compare T2 and T4. The outcome, Boolean outcome will still remain the same. Now what is the advantage of doing that? The advantage of doing that then is that I can, that's one, I'll come back to that advantage. But the whole point here is because this value is moving in locked fashion, I should be able to write T4 is equal to T4 minus 4, and here I should be able to write T2 is equal to T2 plus 4. There are more multipliers on architecture, there are more adders on the architecture than there are multipliers. Multiplication is an expensive operation. Addition is a cheaper operation compared to multiplication. So this optimization says I want to reduce the strength of the computation. So wherever I can replace a multiplication by addition, my program can be expected to be more efficient. So I would like to replace this T4 is equal to 4 star j by T4 is equal to T4 minus 4, and this T2 is equal to 4 star I by T2 is equal to T2 plus 4, but for that I will have to initialize the values here. Okay. Now I can do that. I can initialize T2 here, I can initialize T4 here, and then I can replace these, and now this comparison can be made on T4 and T2, and then by doing that I don't need the variables I and j in the loop at all. I can get rid of these assignments I is equal to I plus 1 and j is equal to j minus 1. I can optimize the program. So this is called strength reduction and induction variable element. I and j are called induction variables. They are the variables that control the values in the loop. So these are, so I can eliminate some assignments, I can eliminate those variables from the loop. I don't need their values in the registers, and the values are later not required, maybe I don't need the values. So in fact, in this program, I don't need the values of I and j beyond this at all, right? So that gives us more efficient program. So not only are we remember here, one computation is executed in a doubly nested loop. Here also a computation is eliminated in a doubly nested loop. So that makes it more efficient. That makes the program more efficient, right? Okay, so yeah, so any questions about this? So many photographs making me feel like I am a groom standing here on the stage and there is a wedding happening and photographs are being taken. Yeah. Okay. So, any question about this? It's clear how we are able to perform. So, I have done this initialization here, right? Okay. So, this is a final intermediate code, and as you can see, lots of slots have become empty. We have eliminated one here in a doubly nested loop. We have eliminated this from the loop. So, this is a final optimized code. Okay. So what are the observations? The observations are optimizations are transformations based on some information. We need systematic analysis for deriving the information. So we don't want to, I mean, we of course looked at things intuitively and we can say maybe we can do it, but compiler can't do that. Compiler has to have a systematic technique for reasoning about, for doing this reasoning. And the goal of today's lectures is to look at how we can reason about these, right? So we've looked at data flow optimizations. There are many control flow optimizations also, but we will not talk about them today. Let me skip this slide. Let me come, so before I come to the next optimization, I want to stop here and take any questions. Anything that's not clear to you? And most importantly, is the purpose of what we discussed, is that purpose clear? Yes? Okay, fine. So let's move on to this. So these were classical optimizations. Now I want to show you a contemporary optimization. I want to show you something that can talk about memory footprint. Okay. So this is, so we're talking about optimizing heap memory usage. So standard memory is generally, or programs is generally divided in these four parts. We have a static data, we have a stack data, we have heap data, and we have code data, right? So where would local variables go here in this part? Which part of the memory would they go? Stack. Where would global variables go? Static data. And if I have x is equal to malloc or x is equal to new, where will that space go? Heap. And the program goes, the text goes in the code section. Wonderful. Now the advantage of heap is the following. It allows us to create data structures whose sizes may vary. When we create something on stack, its size cannot vary. Okay. So its size may vary. More importantly, the data can outlive the procedure, outlive the invocation of the procedure that created that data. With stack, if you allocate on stack, it's a stack frame of certain function f. When f is over, that data is gone. Whereas we would like a situation where data is created by f, stays in the memory, even if the invocation of f is over. I am creating a tree, I am creating a linked list, I am creating a stack, creating something in the memory. So I have a create function which creates a node. After that function is over, I want the memory to remain there, and therefore the logical place for that is a heap. Okay. So heap provides flexibility of lifetime and the flexibility of sizes, but that comes with a cost. That comes with a cost because I don't know how long is that memory needed. Okay. So in order to manage the heap memory, we have to ask when to allocate and we have to ask when to deallocate, right? When to allocate is something that we know, we write in the program. You know, I have x is equal to malloc or x is equal to new, or in functional languages, whenever a new scope begins and I have cons happening there, a new location is created. When to deallocate is the main question. In C and C++, we have to explicitly say free or delete. In Java, what we have is automatic memory management, and that's called garbage collection. Okay, the locations that are not required anymore can be collected by a garbage collector. Okay, now let's talk about manual deallocation. So it turns out that there's this notion of memory leak, which is you have allocated a memory location, it's not being used and still continues to be occupied. Okay, and over time it accumulates, and that's one of the reasons why, if you may have seen, at least until a few years ago, if you have a desktop running on your laptop or PC, a GUI running, sometimes it freezes because perhaps there's a memory leak. Memory is continuously being allocated, program is executing, and at some point of time you run out of memory, you don't have free memory to allocate, and therefore it just freezes. There have been lots of tools to assist manual plugging of this memory, and if you talk to any acquaintance, any relative, any friend in the industry, you will realize that memory leak is an industrial reality. Almost 10 to 20% of the effort, last development effort, goes in plugging memory leaks. This is a genuine problem. Okay, all the leak detectors are kind of dynamic. They can't tell you statically that this is going to happen on the program. You have Valgrind, etc. There are many tools. uh, they're good, but they're still not good enough. Okay, let's talk about automatic deallocation, so which is garbage collection. The idea is to retain active data structure and deallocate inactive data structure. The $1,000,000 question is, what is an active data structure? So the way it is defined is, if an object does not have an access path, that is, if an object is unreachable from a variable, then it is inactive. Okay, that's called garbage. You may have come across these terms, garbage and dangling pointer. Garbage is a location that doesn't have a pointer pointing to it, and dangling pointer is a pointer that doesn't point to a valid memory location, right? So we have this definition of garbage, right? Do you all agree with this definition of garbage? This is how it has been defined? Yes or no? Okay. The important question is, what if an object actually has an access path reaching it? What if an object is reachable but actually not used? It's possible. I may have a location which is reachable from X, a pointer P, but maybe the program doesn't use it. A simple example would be, let's say I'm writing a compiler. I have a symbol table. In my symbol table, I have type descriptor, type information. Okay, I have assigned the offsets to all variables. So I know that this takes 4 bytes. So next will begin +4. So after that, I don't need type information. After a certain point in my compiler, I don't need type information. But this location is still reachable from my symbol table pointer. It continues to be held. It is reachable, but it is not used. That is what should be garbage, but that is not how it is defined. And there is a reason for it, and reason is convenience rather than concept or technology. Okay, let's look at this further. So here is a program. I'm using Java style statements here. So we have references on stack, and we have objects on heap, and we have this program which does something, and P and Q are locations. P and Q here are not reachable from a source variable, so P and Q are considered as garbage. Everything else is considered as a useful data structure, useful data in the memory. Any garbage collector, even the state-of-the-art garbage collector, as we speak now, the best garbage collector can only collect P and Q. No garbage collector can identify anything because all other locations are reachable from X and W. However, we can examine the program a little more carefully. Let's assume that this condition is false. We are making assumptions, we will overcome these assumptions, but we are making these assumptions just to understand what could happen. So let's assume that this condition is false, which means that X is equal to XPTR, this assignment will not execute. this assignment will not execute, so x will remain here. And therefore, if you look at the rest of the program, we are dereferencing x.lptr in statement 4. So we are going to read this location, and then the y will start pointing to I, and then we are accessing y.lptr. So we are going to access this location. So these are the locations that will actually be used in the program. Other white locations will not be used, although they are reachable. Of course, it's under the assumption that the condition is false. Do you agree with me, or am I making it up? You agree with me? It's a reasonable thing to say. But we made an assumption that condition is false. So now let's say maybe condition is true. We at compile time we don't know whether it's true or false. So we have to assume both the conditions. So let's say if the condition is true, then what will happen? Which locations will be used? Can you tell me? X will move rightwards by one link, and therefore will end up using B, F and J. Right? So at compile time I do not know which locations are going to be used. But even if I were to make a safe approximation of either it's true or false, both the things are possible, then I know that only blue nodes are the useful nodes. White nodes must be considered as garbage, but they are not considered as garbage because they are reachable. It should be possible for us to have a technique whereby we can reclaim the memory of the white nodes as well. No garbage collector can do it as of now, because of a very simple assumption that everything that is reachable is useful. But everything that is reachable need not be useful. That's the point that I'm trying to drive home. Right? Okay. So let's skip over these details. So there's something called SRMIST folk wisdom, which says that make unused memory unreachable by setting references to null. And the question is, how do we do that is the main thing. So let's now try to see whether we can actually do something about it. In order to complicate the matter, I have changed if statement to a while loop. Okay, this was if, now I have made a while loop, and now we are making an assumption that if the while loop is not executed even once, then these are the locations that will be used. Right? Do you see that? Right? If while loop is executed once, then what will happen? This blue wave will move rightwards by one link. Right? So what will happen is we will end up using these locations. If the while loop is executed twice, then we will execute these. Right? So we do not know at compile time which locations will actually be used. Right? And that's the reason why garbage collectors assume that everything that is reachable could be used. Now we do not know at compile time how many times this while loop will be executed. We are doing static analysis, so we do not know. Right? So here is a problem. There are these locations, I know for sure that many of them are not required in the program, but I have no way of mapping this dynamic information to a static abstraction through my analysis. I cannot know at compile time, or so people thought, that we cannot know at compile time that we can do this. Okay, that was the thought process going on in the minds of people, until a certain person who is now Professor Ameya Karkare, who is going to teach you tomorrow, came to IIT Bombay, did his PhD and said, no, we can do something about it. And that's what we are going to look at. Okay. So what is the problem here? The problem here is when we talk about static and stacked data, when we talk about static and stacked data, when I say X, I know which location I am referring to. I know the offset of X. If it's a local variable, I know its offset from the frame pointer. If it's a global variable, I know its address. But when I am using X to hold the address of a heap location, the mapping between where X points to keeps changing. So X may point to this location at some point of time, X may point to some other location at some point of time. So at runtime, the mapping between the name of a location and the actual address, that mapping keeps changing for heap. Whereas in case of stack and static data, that does not happen, right? So this is a problem, okay? So what did we do at IIT Bombay? Here is our solution. So our analysis inserts these nullification statements within the code. Okay, and we want to see why it works. Unfortunately, we will not be able to see how we obtain this. It's a very beautiful analysis called heap reference analysis that I teach in my course in the 10th week of the course. So obviously it's beyond the scope of this winter school, but I still want to show you, give you some intuition about what we do. Okay, so this is a program, and now first of all, let's see whether it works. Okay, so here is the instrumented program. All gray statements are inserted by our static analysis, and let's recreate the same situations. We are saying while loop, assume that while loop is not executed even once, okay, and we will see what is the effect of these statements that have been inserted in the program. Okay, so I will highlight the statement one by one. So the first statement, forget about yz equal to null. The first statement, w equal to null, is going to cut away this link, right? W will cease to point to this. Don't ask me how did I obtain it. I'll give you an intuition about it later once we have seen through this. But this will be the effect of the assignment. Okay. Now I am assuming that the while loop is not even executed once. So therefore this statement will not be executed. Therefore I will jump to this statement after 3. Right. So therefore the next statement to be nullified is x dot rptr, the green statement. X dot rptr will be nullified. X dot lptr dot rptr will be nullified. X dot, these are the two locations that will be nullified. So I'm going to cut this link through my instrumented program. Okay, make sense? This is what the execution will be, right? Then I come to the next statement. So I'm going to nullify x dot lptr dot lptr dot lptr. Then I'm going to nullify x dot lptr dot lptr dot rptr. That's what I will nullify. Okay. Now y will start pointing to x dot lptr. So y will start pointing here after this statement is executed, after which we will nullify x dot lptr. So now the program after statement 4 looks like this. This link will go away. Okay, and then we will nullify some more links. By the time we reach statement 5, which is where we have to do new allocation, which is where a garbage collector may be invoked, the memory looks like this. All nodes that are unused have been made unreachable. Right? We'll talk about that. We'll talk about that. It's a good intuition. So her intuition is that we reach a reachable place, and then based on some probability we decide whether the next place is reachable or not. But we'll come to that. But there's a bigger question. I expected someone to ask that question. I have made this assumption. I don't know whether this assumption is true at compile time. Maybe it's executed once. Maybe while loop is executed twice. What will happen? Will it create exceptions? Will we have a null pointer exception here? The program remains same. My claim is the program remains same. Program is not generated taking into account the number of times the while loop is executed. We'll come to that. Yes and no. Yeah? Yeah. Oh, I see. Okay, okay. Okay, okay, okay. Yeah, maybe you can repeat your question and then I'll repeat my answer. Yeah, no problem. Yeah, 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 please do.
Okay, so what I said was, so previously you mentioned induction variable. So similarly, we'll find something that is not changing, that is controlling this loop, the control flow of the loop. Based on that, we will again trace it without executing the loop and nullify all the edges.
The answer is yes and no. Your intuition at a very abstract level is right, but that's not exactly what we do. Or we do something even more beautiful. I'll come to that later. But the first question here is, suppose I execute the loop once, will the program create an exception? I want a clear answer, yes or no. I don't want an answer maybe. What do you think? Yes? How many of you think it will create an exception? Please raise your hand. How many of you think it will not create an exception? Please raise your hands. Do I have to ask the third question? Exception meaning I am dereferencing y.lptr.lptr and this location doesn't exist in the memory because it's been nullified perhaps by previous location. I'm nullifying some links here. What if I have nullified this link and I'm trying to access RPTR of this? That will create an exception. Accessing a field of a pointer which is null will not give you a location that you will be able to access. That's a null pointer exception. So those of you who think it will not create a null pointer exception, I want to hear your opinion. Even if it's guess, it's fine to say I just guessed it. I don't know what the reason is. It's okay to say that. No problem, but I still want to hear. What is the basis of your guess? Do you have a basis of your guess or just some intuition? Or you could always say, because you have the program here on the slide, if you create an exception, you won't show it. That may be one basis, but okay. Let me give you, yeah, you want to say something? Mike, can somebody? Yeah, can I have volunteer here moving around? Sorry, I'm bothering the volunteers. Actually, it's not me, it's the live streaming that's bothering them. Yeah. But I have nullified pointers assuming, yeah. So the question is, he says that all the pointers that are not being used have been nullified. But this nullification assumes that the loop is not executed even once. If the loop is executed once, is this the right nullification? That's the question. Okay, the answer is something very interesting. The answer is, I had already given you a hint before, that if the while loop is executed once, the whole train will move rightwards by one location. What does that mean? It means that if the while loop is executed once, I will not nullify these locations. Instead, I will nullify these locations. Because I am nullifying LPTR and RPTR out of X. The important point is this: the trouble that the rest of the world had with heap analysis was they were asking a question, where does X point to? What address does X hold? Now that is not a program invariant, that is a variant of the program execution. It varies from execution point to execution point. X may hold the address of this location, X may hold the address of this location. So that's a wrong question to ask. When we do research, it's very important for us to first find out what is the right question that we are asking. So the question, it took us, before Ameya came, it took us one MTech project and 1.5 years to realize that everyone is asking a wrong question. The question, where does X point to, is a wrong question. What is the right question? The right question is, am I accessing RPTR link out of X, or am I accessing LPTR link out of X? I don't care where X points to, because I don't know. I can't know. It's a runtime information. What I can know is, regardless of where X points to, does the program access LPTR or does the program access RPTR? That is a program invariant. That is a program invariant because the programmer wrote it. The programmer wrote in the program that when I reach here, I am going to access RPTR out of X. I don't care, and I don't need to care where X points to. All I need to care is, out of X, am I accessing LPTR? Am I accessing RPTR? That is the invariant of the program. Static analysis can discover invariants of the programs, things that do not change over program execution, right? The moment you start asking this question, now I know here that I am not accessing LPTR and RPTR out of X, so I can nullify. Doesn't matter where X points to. Effectively, these nullification statements ride the execution of the loop. Wherever X points to, maybe X points to somewhere else, but when I reach here, I'm always going to nullify RPTR out of X. I don't care whether X was here or here or here. I'm going to nullify RPTR out of X because the programmer said that I'm not going to access RPTR out of X. That is the idea. The rest of the analysis is essentially trying to find out which links are nullified out of which variables and not which variables point to which locations. That is the key idea. Okay, so I don't care how many times the while loop is executed. For this program, there will be no exceptions. There are other situations that are required to guarantee no exceptions. Many interesting things to be done, but we would not be able to go into the details. So the observation is that we might say the node I is live. I am accessing node I, but a link to node I is not live. So we do not talk about whether a location is read. We talk about whether the address of a location is read in this pointer. We talk about the liveness of links, not liveness of nodes. That's the first observation. Second observation is what I said just now, the memory address that X holds when the execution reaches a given program point is not an invariant of program execution. Okay? Whether we dereference LPTR out of X or RPTR out of X, that is an invariant. That is something that the programmer has specified. So we should focus on that. So when we do program analysis, particularly when we do static analysis, we should try to abstract out intuitions, ideas that talk about what will not change over the program execution. And then can we abstract them? Can we find information about them? And there is a plethora of information that we can collect, and there are lots of interesting things that we can do. So for example, this analysis reduces heap memory usage simply by changing a question. Instead of asking where does X point to, we ask a question, am I accessing RPTR out of X or LPTR out of X? Okay. So static analysis can discover only invariants. More importantly, it can discover only some invariants, not all invariants. Static analysis, theoretically speaking, is in general undecidable. Do all of you know the meaning of undecidability? Do you know? Does anyone know? Is there anyone who does not know what undecidability means? Undecidability is not, I am not decided whether I should take this bus or that train. That's not undecidability that I am referring to. Undecidability means, when we say a problem is undecidable, it means that there cannot exist an algorithm to give a precise answer to it in all situations. I am not saying there does not exist an algorithm. I am saying there cannot. So it's not that maybe some smart guy will come and solve that problem. No, that problem cannot be solved. Theoretically, it's been proved that we cannot find a solution. We cannot have an algorithm that will give us the correct answer, exact answer in all situations. So what we do is we find out some approximations. In most situations, we give correct answer, but in some situations, we give a conservative answer. So static analysis is undecidable. So we cannot find all invariants. We may be able to find only some invariants, right? So these are the two optimizations. Time for us to break for tea. So we will stop here, and we will after the tea we'll look at the observation that we have made and try to answer this question: what is program analysis, right? So let us stop here.